So I'm going to start with this that I've already prepared. It's just about the first week that we had in maths, and it's just all about more complex functions, as you can see here. So the first thing we started with was the modulus function, which, as you can see here, definition. So if you ever see this symbol, it means modulus, and what it's defined as x if x is greater than 0 or equal to 0, and minus x if x is less than 0. Over here you can see a few graphs that I've drew just to show what the function looks like. So over here you have the line of y equals x. You can see that when it hits 0 or goes below it, we actually take minus x. And then you can see down here what we end up with is the line of y equals minus x and y equals x. Some things to note, at the y coordinate y, on this graph in particular, because it's y equals x, this coordinate here is xy, and this one here is minus xy. As we have two gradients, we do not take dy by dx. We could split these into two different equations if wanted, and we do that later on when we come to solve them. On the right, you can see that we've got a quadratic, so it's pretty much the same. All I would state here is that this one goes below the x-axis, so what we do is we take this coordinate, put it up here, and then when we hit the x-axis, we just draw the opposite to make sure we hit them points. Same as before, yep, down here. That's basically just what I said. Okay. So, to solve a modulus function, so say mod f of x equals a, where a is an element of the real numbers, basically just means it's a real number, so we're not using I or anything. Let's solve this equation. So we got 6x minus 5 equals 4. So what we do is we split it. So y equals 6x minus 5, which equals 4. Get the y in there. We're splitting into two equations. I've just been lazy. So it would be y equals 6x minus 5 and y equals 4. And then sketch each one. So you got mod 6x minus 5 here. And you got the minus of that. And then you sketch the y equals 4 here. Just some quick coordinates I wrote here. When y equals 0, x equals 5 over 6. So this bit down here is 5 over 6. And this line here, this equation, is y equals minus fx, which is actually y equals 5 minus 6x. So I'm going to notice we intersect on both equations. So to set both equal to y equals 4, as you can see, that's what I've done here, and then I've just solved down. You end up with these two answers. And if I go down a little bit more, you should see I wrote some notes. So this first one on the right, quadratics and higher powers can have a different number of solutions. What do I mean by that? Well, if this was a quadratic, as you saw before, it would come down, and say it was a really steep quadratic, it's coming in like this. It would come down and it would hit like the y-axis down here, so it would actually bounce all the way up, doosh, doosh, but then it would come back up, so you'd intersect 4 times. If this wasn't as steep, so if I just do this again but in green, so if this wasn't as steep, and it came in like this, barely hit it, or just evenly hit it, it could hit once, go up and out, then you get 3. So you don't really know. That's why we sketch. Another thing here is, and I drew all over it, but there is a triangle in here. You can see it. It's blue. So there is actually a triangle here, which is what I've drew here. So you got 5 over 6 here. You'll notice that the 2 points where we intersect are equidistant from the root. That is only true, I believe, with these linear ones. But you can just take coordinate geometry. So if you work this one out, and you find out the difference here, subtract it from that midpoint, you should get your x coordinate there. It only works in some situations. If you look at it geometrically and your graph's accurate, that's fine. If not, then I would probably just avoid it. What else do we have? Oh, yeah, here we go. So we've got composite functions, that was next. So in simple terms, it's just a way of combining functions. Let me just get my red bar. So it's just a way of combining them. If you think with Python, if this little bit here, what we would do is we would first get an input from somebody, are we okay? And then we would print the response from that input. So if we answered yes, it would say yes. This is basically composite functions in action. It's quite interesting. I found it just quite nice. But yeah, nothing much more to say there. Go a bit further down. Just a bit more of a mathematical definition. So the composite of two functions, g and f, is a new function we get by performing f first and then performing g, expressed as g of f, g composed of f. G composed of f of x equals g of f of x for all of x. Essentially, this is from my lecture actually. Quite a lot of this is, but I think that's specifically quote unquote from the lecture. One thing to note is g of f does not equal f of g. That would be silly. If you take the 3x plus 5 here and you do the 3x first, you'll get a different answer. If x is 1, actually that's a bad example. If x is 2, you would get 6 plus 5, 11. And over here, if x was 2, you would get 7 times by 3, 21. So you get different answers. So they are not the same. Inverse functions. So a function is said to be inverse if it's satisfying the expression where f of x and its inverse of x just gives you x. Over here is another way of expressing that, where f of g of x equals x, then g equals the inverse of f. So something I just really quickly forgot to say and glossed over is that some really common examples of inverse functions are integrals. So anything integrated with respect to x, and dy by dx. Ooh, I started dy. So bad. And some other ones are maybe the common trigonometric ones, sine to the -1 and sine. Tan to the -1, tan, etc. Squaring and square rooting, another example. So a function can only have one inverse. This is a small little proof. It involves a bit of, I don't really know what I'll call this, to be honest. But I had to look it up online anyway. It is quite complicated, but I do understand what it's trying to say. So this here is an identity function. It's the identity function. And it's basically just saying that if we put something into this, we will get the same output no matter what we put in. So if it's 2 and we put it into this function, we will get 2 out. If it's 4 triangles in a circle and we put it into this function, we will get 4 triangles in a circle out. So first of all, we assume f of g of x equals f and f of h of f equals x. So we're basically saying that f has 2 inverse functions. One is g of x and one is h of x. Or f of g, f composed of g equals f composed of h, which equals e. So then let's reapply g to both sides. We get g composed of f composed of g equals g composed of f composed of h. This is all a mouthful. Or this, if it makes it a little bit easier to understand. Oops. So if you remember that g and f are inverses, so g composed of f equals e, Well, over here we have G composed of F and G composed of F. Therefore, G composed of F of G equals E composed of G, because this is E, and G composed of F of H equals E of H. But if you look up here, when I wrote down this identity function up here, E of X equals X. So E composed of G equals G, and E composed of H equals H. And if you remember up here, these were both equal to each other. Therefore, G must equal H. Therefore, there must only be a singular inverse. And that is that. Yep, so I know it's not the most entertaining YouTube video or anything, but it is here for my own revision. And if anybody else finds it interesting, that's nice. But yeah.